All right. So Shalma, let's say you're some kind of adventurous archaeologist, like an Indiana Jones-like figure.
Yeah, it's my night job.
Yeah, as one does.
Yeah.
And you go into some like ancient Temple of Doom like, building. And no one's been in this place, you're sure, for like thousands of years. And you open that door up, and surely what you expect to see is some place that's in total decline and collapse and decay, neglect. Thousands of years will just do that to anywhere.
Yeah, I mean, I 100% expect to be booby-trapped, for sure.
Of course, all those darts and snakes and whatever, yes.
Right.
But in addition to that, you expect the place to have fallen into a lot of disrepair. So how would you feel if you, upon opening that door, instead of that, you see a place that looks like just pristine and everything's clean? Not only is the stone in good shape, but the wood is still solid and exactly like new. And then you notice like there's some fresh food over there, and there's some dogs and cats running around. There's some fresh cheese and apples. That just doesn't make sense, right?
No, that would feel extremely cursed. It almost has like Pan's Labyrinth.
So in terms of physics, the explanation or the reason why you would never expect to see something like this in this circumstance boils down to what physicists call the second law of thermodynamics. The second law says that unless you use energy to prevent it somehow, the entropy of everything will increase as time advances. In other words, things tend to fall apart or decay unless energy is used to prevent that from happening. So over thousands of years, we'd expect our Temple of Doom place, would have fallen into total neglect and decay and disrepair. And you shouldn't find things like, brand new looking wood and fresh fruit and cats and dogs and whatever. Without new sources of energy, stuff like this should have just died and decayed long ago. Here's where it gets all very weird.
Okay. Has not been weird yet, for sure.
Yeah,
this is a totally normal physics podcast. So.
When some cosmologists look at our universe, they have a reaction that's pretty similar to this Indiana Jones-like person walking into this hypothetical Temple of Doom. They look at our universe and it just seems way, way too ordered. It seems to have way too little entropy. And this has led some of these physicists to consider these strange things called Boltzmann brains. And I'd go as far as to say that of all the things we've talked about in the couple of years we've been doing this podcast, Boltzmann brains are probably the single weirdest idea or possible thing that we'll ever talk about. And that's saying a lot.
So today, a deep dive into this very strange idea of Boltzmann brains. Stick around.
This episode of Why This Universe is supported by Wondrium. Wondrium is a mind-blowing subscription service that offers thousands of video and audio courses on a huge range of topics. I've been a big fan and regular consumer of Wondrium's content for the last 15 years or so, and over that time I've listened to dozens of their courses, including ones on history, philosophy, literature, math, and science. For me, it's like taking an intro-level university course from a great professor on a subject you've always wanted to know a lot more about, but without the big tuition fee and all in the comfort of your own home or daily commute. I just started listening to a course on Wondrium called The Great Questions of Philosophy and Physics. Over 12 lectures, this course explores the relationship between physics and philosophy, asking questions like, do the things that physicists discover in their experiments necessarily exist, or are they just convenient ways for us to conceptualize our world? For someone like me, this kind of course can really be a great thrill. So if you want to learn about the philosophy of science, or just about anything else for that matter, give Wondrium a try. You can sign up for Wondrium now through our special URL to get a free month of unlimited access. Just go to wondrium.com/universe. That's wondrium.com/universe.
You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. My name is Shalma, and I'm a PhD student at NYU.
And I'm Dan Hooper. I'm a theoretical astrophysicist at Fermilab and at the University of Chicago. So the story we're going to explore today starts with this Austrian physicist, Ludwig Boltzmann, who was one of the key figures in the development of the field of thermodynamics. So among other things, Boltzmann work really clarified what entropy is, and he was able to explain why the second law of thermodynamics, what it really means and why it has to be built into the laws of physics. So in 1896, Boltzmann wrote this interesting paper where he pointed out that our universe seems to be a lot more orderly than it seems we should have expected. In other words, its entropy is much lower than he thought it should be, all else being equal. And at the heart of Boltzmann thinking is this idea, the second law of thermodynamics, which states that the total entropy of any closed system will tend to increase over time. You can think of entropy as like a measure of disorder. So you can understand the second law as saying that things tend to become more disordered. Eggs sometimes break, but they don't spontaneously unbreak and kind of reconnect into, unbroken eggs. Glasses, if you drop them, they'll shatter into shards. But if you throw a bunch of shards at the ground, they don't jump together into an intact glass, et cetera, et cetera, et cetera. These are all examples of the second law of thermodynamics playing out in the real world. And it kind of is a universal law. It has to follow from the statistical laws of classical physics. So you can use energy, if you set it up in the right way, to make things become more ordered. In other words, you can use energy to work against the second law. But when you do this, it increases the overall entropy of the system.
For example, I could pick up Dan's broken shards of glass and glue them back together into a vase, seemingly decreasing the entropy of the vase. But in order to do that, I need to eat and metabolize energy and release high entropy heat back into the universe, meaning that I'm not actually able to get around the second law of thermodynamics.
If you take any system, any closed system, and you wait long enough, just give it enough time for the entropy to go up and up and up, it should eventually reach a maximum state of entropy, the most entropy that stuff can have. And we call this a state of heat death. Once you're in this state of heat death, you can't do, really anything that's interesting. You can't do metabolism. You can't, have any kind of computation or calculations or thoughts. All that stuff is impossible in a state of heat death or a state of maximum entropy.
So once the sun is long dead and all of the universe's heat is distributed around in a structureless soup, then there'll be no food for me to eat as an energy source to use to think, let alone to piece a glass back together with.
In a state of heat death, a state of maximum entropy, every possible source of energy you could use has been distributed throughout everything in some roughly equal way. There are no reservoirs of energy out there to use to do anything interesting. Everything is just in a total state of equilibrium, and nothing in that state of any interest could ever happen. So when I was first learning about the idea of entropy and the second law of thermodynamics when I was a physics student many years ago, I was confused about this idea quite a bit. After all, when I look at our world, we don't seem to be necessarily in a state of ever increasing entropy. I mean, sure, the breaking glasses and breaking eggs, all that looks like it. But, new living things keep being born and some things decay while some things get built. So it looks like our day-to-day lives are breaking the second law of thermodynamics.
Right. You'd also think about evolution maybe and the fact that more complex life is developing over time.
In certain pseudoscientific creationist websites will argue that the evolution violates the second law of thermodynamics, which of course it doesn't. But this is exactly the thing that the student version of me was confused about at the time. The resolution to this, the explanation that I wish I'd understood better at the time, is that the power of the sun, the availability of sunlight, is being used by the Earth's ecosystem constantly to keep its ecosystem in a state of relatively low entropy. So the sun's entropy is going up and up and up and up, and we kind of cannibalize on that, keeping our ecosystem's entropy low through the use of that free energy, that available energy. But if you took the whole solar system as a combined system, you'd still find that the total entropy of that, including the sun, is going up with time. So we're not violating the second law here. We're just moving entropy from the sun to the Earth and its ecosystem. So in the very long run, billions or trillions or whatever years from now, the sun and all the other stars will run out of fuel. And they'll stop producing things like sunlight, and all the planets around all the stars will go into a state of heat death, right? Well, everything will decay. Life won't be possible. Doing computations won't be possible, and doing metabolism won't be possible, and ever putting together a, perfectly intact egg or glass will be impossible. They'll all have decayed away. I know it sounds kind of morbid, but in the long run, nothing can escape the specter of increasing entropy.
Yeah, it's like entropy as a law of physics kind of codes death into the universe. No
Sadly, that does seem to be the end game of anything that's subject to the second law, which is everything. Let's go back to Ludwig Boltzmann with this in mind. In his day, so we're talking, 120, 130 years ago, something like this, most physicists thought that the universe had probably been around forever. They imagined that space was just this fixed thing that never starts or ends. So, the universe was infinitely old and it would persist infinitely far into the future. After all, we didn't have general relativity or any of Einstein's ideas yet. So the idea of how space could change or come into existence or cease to exist, none of that was out there. So we didn't really have any way to even conceptualize the start or end of time. So most physicists just thought the universe would exist forever. And if the universe really was eternal, infinitely old, then there was already in the past an infinite amount of time for the second law of thermodynamics to have done its thing. And Boltzmann looked at that and said, well, then we should all be in a state of heat death. And we shouldn't have things like living organisms. We shouldn't have things like stars that haven't run out of fuel. We shouldn't have things like unbroken glasses or unbroken eggs. This universe doesn't look like it's in a state of heat death, and he didn't understand how that could be. So he wrote this paper in 1896, and he proposed two possible solutions to this problem. The first solution he proposed is that maybe our universe isn't infinitely old. Maybe it started out in a state of very low entropy and it's slowly increasing entropy, but it hasn't maximized its entropy yet. It's not in heat death yet. It will be someday, but it's not there yet. That's kind of the conventional view of modern cosmology, by the way. That's, we think there was a big bang, started out in very low entropy. It's in higher entropy now, and someday it will be in higher entropy still. Boltzmann's paper had a second solution to this problem, though, that he proposed. And he said, well, and I'll just say this is a lot more weird. He said maybe, just maybe, our whole universe is already in a state of maximum entropy and heat death. In a universe like that, low entropy things like unbroken eggs or unbroken glasses or metabolism operating living things, all that stuff should be very, very rare. In low entropy events, like, having thoughts or, organisms, coming and being born and things like this, these things should almost never happen. But notice I didn't say never. I just said almost never. So even in a universe that's in a state of total heat death, there will be exceedingly rare instances in which those sorts of things can happen just by random chance. So maybe once in a trillion years, there'll be enough atoms that just happen to come into together, in some random way, leading to them coming together and being a metabolism, performing living organism. It's not impossible. It's just very, very unlikely. But now bear in mind, our universe in this picture is infinitely old. So anything that can happen, even if it's ridiculously unlikely, that will happen an infinite number of times, given an infinite amount of time. So if Boltzmann was right about this, if the second proposal of his was right, then the vast majority of the total universe, the utterly vast majority, almost in all of it, is totally devoid of anything remotely interesting. Almost everywhere would be in a state of maximum entropy and heat death. But after an infinite amount of time, occasionally, actually an infinite number of times, complex stuff will just happen by chance, no matter how unlikely it is, given an infinite amount of time to wait for it to happen. So in this picture of Boltzmann's, our whole solar system and our whole ecosystem and everything is just kind of a cosmic accident of vanishingly unlikely coincidences happening. But, it's a logical possibility, and I think Boltzmann was right to point it out. Boltzmann's idea stayed out there for decades. It wasn't, followed up by many people. I don't think it was talked about very much. It certainly wasn't a hot topic. But people started to chime in about some variants to this over the years. In 1931, the astronomer Arthur Eddington pointed out a pretty big problem with Boltzmann's original idea. What Eddington pointed out was that if the universe were in a state of heat death, the odds of something coming together or some event taking place by random chance is exponentially related to its complexity. So, like, roughly speaking, if something is 10 times more complex, it's not only 10 times less likely to happen, but it's, e to the 10 or something times more unlikely. It's vanishingly unlikely. So Eddington pointed out that if the universe is in the state of heat death, then what we should see is, kind of the minimum complexity state that could possibly exist that would lead to conscious experiences. And that wouldn't be a night sky with millions of stars. It might be a state with one star, or maybe even something simpler than that. And that's not our universe. So at least in Boltzmann's original idea, the second explanation doesn't seem to carry much water.
I just want to put in, just so people get the idea, with the example of it being 10 times more complex, e to the 10 is actually like 22,000. So
exactly.
It would be like 22,000 times less likely.
And our universe or our ecosystem or something isn't just 10 times more complex than the minimum that it would take to have some thoughts. It's many, many more than 10, and e to some giant number is some unbelievably enormous number. This shouldn't be the universe we see around us if Boltzmann's weird explanation were the right one. So things developed as cosmologists learned more about our universe in the middle of the 20th century. And it started to seem in that era that Boltzmann's first solution looked pretty plausible, namely that there was a big bang, the universe began. Some point in the distant future, the universe would collapse, undergoing something we call a big crunch, kind of a big bang in reverse. So we'd have a finite amount of time that our universe would exist for. And in that finite amount of time, entropy would go up. But, ultimately, all those weird, super unlikely things would never have enough time to happen. So that seemed very plausible, at least for a while. More recently, though, cosmologists have more precisely and carefully measured how our universe has expanded over time. And it no longer looks like our universe is ever going to end. It's not slowing down. It doesn't look like it's going to collapse. In fact, it's expanding faster than it used to. And, we could be wrong, but all indications are it's just going to keep doing this. And if that's the case, then we have an infinite amount of future to contend with. And if that's true, then all those super, super unlikely things should happen an infinite number of times. And that gives us a new version of Boltzmann's old problem that we have to face. We have to contend with this. There has to be an explanation. Another thing that's really important that's changed in our understanding since Boltzmann's day is we understand quantum physics. Boltzmann died before discovery of quantum physics. So Boltzmann had in mind a universe where atoms were moving around at random and occasionally making complex things. And in a universe that's expanding, that might not be important because the density of those atoms will go down and down and down as the universe gets bigger. But quantum mechanics gives us another way for random things to come into existence. In particular, through quantum effects, particles and energy can briefly kind of come out of the vacuum, just out of nothing. And this happens all the time, anywhere in space. Like usually it's things like an electron and a positron exist suddenly out of nothing, and then they annihilate and disappear a fraction of a second later. But there's a small but finite chance that whole atoms could pop out of existence, or groups of atoms, or a whole person, or a whole planet, or a whole solar system. These things have a very, very, very small, but not zero chance of happening according to the laws of quantum physics.
Right. I was going to actually say, after you described the first part, like, okay, sure, our universe is going to like expand without limit, but like everything's going to get really far away from each other. So like, that probability is going to diminish. But I forgot about quantum mechanics.
Quantum mechanics will get you every time. So picture what this looks like. So let's say we have cosmology right, and there's going to be an infinite future with almost nothing in space, but all the same, there'll be an infinite amount of time. And quantum physics, given enough time, can make anything spontaneously pop out of the vacuum. That means that in the infinite future history of our universe, an infinite number of things will spontaneously pop into existence. And that means an infinite number of times, cups of coffee and eggs and glasses and all these things will come into existence. And an infinite number of times people will pop into existence, or brains that are capable of thought. Infinite number of time planets and solar systems and whatever will pop into existence.
I don't like where this is going.
I think you can start to see where this is going, Shalma.
Yeah, am I just a brain that popped into existence somewhere in a vat that is making all these memories up?
Except for the vat. Yes, yeah. Exactly right. So if a brain that's capable of holding a single human-like thought can pop out of existence in out of the vacuum of quantum space, then in an infinite amount of time, future time, that will happen an infinite number of times. Now, this is very unlikely, okay? So one estimate I've seen is that in a amount of space equal to the observable size of our universe, it would take 10 to the 50 years for this to happen once. That's 10 to the 50th power. So that's the biggest number I've ever seen expressed in anything. So it's exceedingly unlikely. But no matter how unlikely it is that this spontaneous brain will come into existence and have a thought for an instant before disappearing, in an infinite amount of time, this will happen an infinite number of times. And since the number of real brains, like the ones that we think are attached to our bodies and everything, since the number of thoughts they'll ever have is big but finite, the infinite number of these non-real brain thoughts that will exist will wildly outnumber the ones from real brains. And we call these quantum fluctuations that produce thoughts Boltzmann brains, and that was coined by the cosmologists Andy Albrecht and Lorenzo Sorbo back in, I think, 2004.
Okay. It's an idea. Yep.
All right. So to put it another way, over the course of cosmic history, there'll be a very large but very finite number of real brains. But there'll be an infinite number of thoughts manifest by Boltzmann brains. So if given this, 99.9999999% of all thoughts that will happen over the course of cosmic history will be Boltzmann brain thoughts. So then you have to ask yourself, how sure am I that the thought I'm having right now isn't the manifestation of a Boltzmann brain?
Can you have a Boltzmann brain thought that is a complex thought that involves understanding what a mic and a computer and a podcast is?
Well, so you don't think all those things at once, right? You think little nuggets of it one at a time.
No, but I feel like having the thought, like I'm recording this podcast, is kind of a culmination of understanding all of these things. Like, it's a one thought I can have because I created the language to describe a podcast. And like within the word podcast, there's like a lot of other understandings that have like formed that one word, that one thought, you could say.
So again, I think the power of just having an infinite amount of time to wait for these complex things to happen. The more complex a thought, the less likely it will be, of course. But in an infinite amount of time, they should all, every thought, no matter how complex, should be quantum, manifest an infinite number of times. All right, so this is all a very heavy and weird idea. But let's take a step back and figure out what we should make of this whole thing. All right, so first of all, let's just make it clear. There aren't a lot of cosmologists out there, I've never met one anyway, who's going to express the view that they think the thoughts they're experiencing are very likely to be Boltzmann brain thoughts. Okay, that's not what these cosmologists are saying. Maybe some of them think it's a possibility, but they don't seem to think it's likely. And the reason we dismiss the possibility that this is really the right answer is that if it were true, then we can't trust anything we think we know about our universe. After all, every memory we've ever had is just the result in this picture of a random quantum fluctuation, kind of like having random bits of a dream. So if you have just a bunch of random thoughts you've dreamt, trying to use that information to find out what the universe is like won't get you anywhere, right? It only tells you about the thoughts. It doesn't tell you about anything else. So in the course of this logic, we've used facts like the universe is expanding. We've used facts like quantum physics behaves the way it does and whatever. In a universe where all your thoughts are Boltzmann brain thoughts, you wouldn't know any of that. So you don't know anything. It just all collapses like a house of cards.
Yeah, I buy that.
Well, okay, so even if we don't think Boltzmann brains really exist in any relevant way, that's not what our current standard cosmological theory tells us should be true. So if we take what we think we know about quantum mechanics and we take what we think we know about the future of our universe, namely that it's infinite, then there should be an infinitely larger number of Boltzmann brains than real brains. And then you have this problem. Then all our thoughts should be Boltzmann brains and everything falls apart. So maybe this apparent contradiction is telling us that there's something wrong about our standard cosmological theory. And that sounds pretty important to me. So looking this problem in the eye and asking, why am I having thoughts that I don't think are Boltzmann brain thoughts, might get us incrementally closer, might be providing us a hint about, the physics of cosmology. Maybe it's going to tell us that the future of our universe isn't infinite somehow. Somehow it's going to come to an end and we don't know how yet, but maybe it's telling us that. Maybe it's telling us there's something we don't understand about the laws of physics that are relevant to this, something, again, we don't know about yet. And all these things could change how we think about this question that Boltzmann posed, more than a century ago. So the point is, I don't think you should walk away from any of this thinking we're probably Boltzmann brains. But the fact that we don't think we're Boltzmann brains tells us there must be something wrong about the way we think about our universe.
Today's episode was produced and edited by me, Shalma Wegsman. My co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. Dan is also an author and has written many books, including most recently, At the Edge of Time, Exploring the Mysteries of Our Universe's First Seconds. Thank you for all your support and for listening to our show. If you want to support us even more, you can subscribe to our Patreon, where you can ask us questions for exclusive Ask Us Anything episodes, as well as get the ad-free versions of our regular episodes. You can find our Patreon at patreon.com/whythisuniverse.